What does it mean for two objects to have the same set of symmetries? So here I've drawn a square and a cross, and I've displayed how they have the same rotational symmetries. What I mean by that is that if you want to look at the symmetries of a square, well, you can do nothing. You can rotate by 90 degrees and it looks the same. You can rotate by 180 degrees and it looks the same. And you can also rotate by 270 degrees and it looks the same. And you can do the same with the cross. You can rotate by 90, 180, or 270. And it kind of looks like the symmetries of a square and the symmetries of a cross are the same. But how do we formally say this? How do we formally show that the symmetries of a square are the same as the symmetries of a cross? To do this, what we're going to do is we're going to introduce the notion of an isomorphism of groups. This isomorphism, we will soon see, encapsulates what we mean when we say that two symmetries are the same. So first, let's review the definition of a group. This is a bit abstract, so if you don't understand, don't worry. We'll go through some examples and clarify what the definition means. But first, let's quickly review it. The definition of a group is this. A group G is a set with a binary operation. So a binary operation is something that just takes in two elements of the group. And again, I'll explain this later. It takes in two elements of the group. That's why we say G cross G, and it spits out another element of the group. Okay, and we say, this is just notation, this dot here. Okay, so it's a group G is a set with a binary operation. So it takes two elements and it spits out one, such that we have these four conditions. The first is closure. Closure says that for any GH in G, we have that G dot H is in G. So if we take any two elements GH in G, that's what this symbol means, in, then we can compose them under the binary operation and we still have an element in G. So the element that is spit out is another element in G. The second is the identity rule. This says that there exists some element E in G such that G dot E equals E dot G equals G for all G in G. Okay, so again, this dot here is just referring to the binary operation that we defined earlier. Okay, and this E is just notation. You can call it whatever you want, but the point is that there must exist some element that behaves this way, so that when you compose that element with any other element, you just get the original element back. So it's a lot like multiplying by 1. The third rule is associativity. Associativity says that if we take brackets in the first two elements, so if we say G dot H, bracket that, dot K, then that should be the same as taking G dot brackets of the next two, so G dot bracket H dot K bracket. Okay, so this is just saying we can pass brackets around and it doesn't change the value of the expression. The final axiom is the inverse rule. This says that for every G in G, so any element G in G, there must exist some G inverse in G such that this is obeyed. So it's saying that there must exist some element. We just denote it G inverse. So G to the minus 1 means G inverse. And again, you can call it whatever you want. It doesn't really matter what you call it. So we could call this A, B, C, whatever, right? It's just notation. So such that G inverse dot G is equal to the identity. So from the identity axiom, it's equal to the identity. And that we can do it the other way. We can also do G dot G inverse, and that's also equal to the identity. So this is the definition of a group. If this doesn't make much sense, you can refer to the video I posted before, but I'll go through some examples and clarify how this definition works. So first, I want to consider the group of symmetries of a square and show that it's a group, just very quickly. Again, I'll do it briefly because I did show it in the previous video. Okay, so I've drawn a little square here. I hope that shows up on camera. And basically what I've shown is that we can have a square and we can rotate it by 90 degrees, and that's a 90-degree rotation. And that's just what this arrow is meant to depict. So I'm going to name the action of a 90-degree rotation. So the action itself, I'm going to name it R. Okay, so whenever you see R, this means rotate by 90 degrees. Okay, then we can see that if we want to rotate by 100 degrees, then it's just R composed with R. Okay. Now, when I write R, what I mean is do R and then do R again. Okay, so this is kind of my binary operation. Okay, I'll put a dot here to make that clear. So, so this binary operation goes from G to G, and I haven't defined what G is yet. I'll get to that. It goes from G to G, and it just is the same as do two actions after each other. Okay. So if, for example, I take R in my group group of symmetries of the square, if I take R and I take another element, I just do one after the other. Okay, that's my binary operation. So what I'm going to do is I'm going to say, if I want to do R and then followed by R, I'm going to call that R squared. Okay. Again, this is just notation. You could call it RR if you want to. I'm just going to call R squared to make this a bit quicker. Or we can rotate by 270 degrees. What would that be? That would be R cubed. Okay. So again, it's just notation. Okay. I'm just calling it R cubed for notation. Doesn't mean anything. Or we can rotate by 360 degrees. Okay. So we could also have R dot R dot R dot R. And this will be R to the fourth. But notice if I rotate by the full 360 degrees, I've essentially not changed the square. And so I'm also going to call this 1. Okay. And we'll see why I call it 1 later. And I'll call this group S. Okay. So our group is S. I'm going to call this S. And S is a set. And what elements does S have? Well, S has 4 elements. It has R, which is just a 90-degree rotation. It has R squared, which is a 180-degree rotation. It has R cubed, and it has 1. Okay. These are the elements in my set of symmetries of the square. Okay. So we have a binary operation for our group S. Do we have closure? Well, let's think about it. I can take any of these elements and I can compose them. So for example, I take R and I take R cubed. So R means rotate by 90 degrees. So if I take R, rotate by 90 degrees, and then I take R cubed, rotate by 270 degrees, do we remain in the set? Let's think about it. We start here, we rotate by 90 degrees, and then we rotate by 270 degrees. Oh, we ended up back here. So doing R and then R cubed is actually equivalent to doing nothing. And doing nothing is our 1 element, okay? So what I'm saying here is that R dot R cubed is actually just equal to 1, okay? And I'm not going to go through every combination, but you can, and you'll see that we do have closure. So no matter how we compose any of these 4 elements, we always end up back in S, and that's what closure is. Do we have an identity? Well, I'm not going to go through this in too much detail. You can pause the video and think about it, but I'm going to tell you that 1 is our identity. So if we do nothing to our square, so the 1 element means do nothing to our square, that's our identity. Okay, think about that. Associativity, again, I'll leave that to you because we did cover this in the last video, but associativity does work. Associativity just means in what order do we take the actions, right? So do we want to take the action as G and then H and then K, or do we want to do G and then bracket H and then K, okay? Inverse, do we have an inverse? Well, I'll just give you a quick example. Actually, I've already given you guys an example because R dot R cubed equals 1, and 1 is the identity. What does this mean? It means that the inverse of R is just R cubed, right? Because if we take R and we multiply by R cubed, we get the identity. And that's what the inverse axiom wants. So what I'm going to show now is I'm going to do the same sort of thing for the cross, and we're going to show how these 2 symmetries are the same, how we can formally say that they're the same. Okay, so I've drawn a cross here, and I've labeled the rotation by 90 degrees as A. So whenever you see A, think 90 degrees. Again, we can do the same thing as we did with the square here. We can say that A squared is 180-degree rotation because if we apply A twice, we get 180 degrees. So again, rotate 180 degrees, this will be A squared, and so on. You have A cubed, and you also have A to the 4th, which I'm again going to label 1, okay? And so what I'm going to say is that the group C, so I'm going to label it C, and I'm going to show to you guys that this is a group. The group C is composed of these elements. Okay, so I'm going to say the group C has these 4 elements, has A squared, A cubed, 1. So these are 90-degree rotation, 180, 270, and then the do nothing, or equivalently the rotate by 360-degree rotation. Okay, my aim is to show that this set C is equal to S. So let me write that down. Okay, so I haven't actually showed that C is a group. You can do that as an exercise, but I hope it's easy enough to see that it does follow all of these axioms. So my aim is to show that the group C equals the group S. Okay, if we can show that the group C equals the group S, then we can show that the symmetries of a square and the symmetries of a cross are actually mathematically the same. Okay, so the question is, how do we do this? How do we show that two groups are the same? Because they don't really look the same, okay? They kind of behave the same, but they don't look the same. This has elements a squared, a cubed, and 1, and this has totally different elements. It has r squared, r cubed, and 1, okay? And they don't really mean the same thing. Sure, a means a 90-degree rotation, and r means a 90-degree rotation, but a means a 90-degree rotation of a cross, and r means a 90-degree rotation of a square. So these are fundamentally different things, okay? It's not so simple to say that, yeah, S and C, they kind of seem the same, so they must be the same. We need to formally show this. Now, before I do this, I just want to give you guys an example of one more group, and you'll see why at the end of this video, why this example is important. Okay, so I've drawn a rectangle here, and what I want to do is I want to outline to you the group of symmetries of a rectangle. So one thing we can do is we can flip the rectangle along this axis, okay, so like this. Flip it like that, and that's a symmetry of a rectangle. It's pretty obvious, right? Let's label this F, okay? F for flip. Well, we can do the same thing this way, okay? We can flip it this way, right? Flip it along this axis, and it looks the same. Let's label this one capital F, okay? What else can we do? Well, we can rotate can we rotate the triangle by 90 degrees? No, because it's long this way, and if we rotate by 90, it ends up long this way. It doesn't look the same, but we can rotate by 180 degrees, okay? So we can do this all the way around. And so what I'm going to call that rotation is I'm just going to call it little r, okay? And then finally, again, we can rotate by the full 360. We get the original rectangle back, and I'm going to call that 1 again, okay? So if we do this, we get 1, okay? So let's label this T for T rectangle, okay? So the group of symmetries of rectangle has 1, it has R, it has capital F, and it has lowercase f, okay? Now, again, another exercise for the viewer is show that this is a group. It's not very hard to show that this is a group. It's actually fairly simple, but it is a little bit more non-trivial than the cross and the square, okay? So you can show that this is a group, but this is a group, okay? Now, let's put this group in the back burner because we will come to this. What I'm going to do now is I'm going to define what an isomorphism is. So I've just written down the definition of an isomorphism. Let's go through it. Again, this is a little bit abstract, so if you don't understand it immediately, that's okay, because I'm going to motivate the definition with the square, the cross, and the rectangle. So an isomorphism between two groups, G dot. So the reason I write this G dot, it just means G is the group and its binary operation. Remember, we have to have a binary operation, is this dot, okay? And another group, H, so I'm going to label the binary operation as something else, just so we can clarify that this binary operation belongs to H and not to G. So there's a star here, okay? So an isomorphism between two groups, G dot and H star, is a bijective map. If you don't know what bijective means, it just means that the two groups have the same number of elements, okay? That's a quick and easy way to know what bijective means. So the two groups must have the same number of elements, and we must have a map phi, so the symbol means phi, from G to H, so it takes an element in G and maps to something in the group H, such that for any two elements of G, so let's say GH in the group G, we have that if we take G dot H and then we apply the map phi to it, then that is the same as if we applied phi to G and H separately and then composed them with the H binary operator. Okay, so I'm going to define a map here, phi, and phi is going to start with the group S. So remember, we defined S here for the square, and I've drawn a little square there in case you forget. And it's going to map to the group C. So remember, C was the group defined for the cross, and I've drawn a little cross here just so that, again, you remember that C is cross. So we have a map from the group of symmetries of a square to the group of symmetries of a cross, okay? And this here just means that we're going to map the element R, so R in the group S, and we're going to map it to A in the group C, okay? So phi of R equals A, essentially, is what this means. That's what this vertical bar means. So is this map an isomorphism? Well, let's think. We need to show that for any two elements, G and H, that if we map G dot H through phi, then we can map phi, G through phi, and H through phi separately and then compose them. What does this mean? So let's try R and R cubed. Okay, what happens here? Well, we require, I'm just going to write this, we need, and so what do we need? According to this axiom, what we need is that phi of R dot R cubed is equal to phi of R star phi of R cubed. Okay, that's what this axiom says, right? You take any two elements, you compose them through the binary operation in their original group. So in this case, we rotate through the dot operator, right, that we defined for the square group. So we do those actions with the dot operator. We apply them at phi. What is that supposed to equal? Well, it's supposed to equal, if you do phi of R by itself, and then this star is the action for the C group, okay? So C star, right? So this should equal to, if we did phi of R star phi of R cubed. This is what we need, okay? Now, let's prove it, okay? So, proof. Before we prove this, I want to understand, what does phi do to every element of the group, not just R, okay? So I want to do this. We know that phi of R is equal to A, right? That's how we define phi. Well, what's phi of R squared? Okay, what is phi of R squared? Well, I'm going to define it to equal A squared, okay? This is my definition, because we haven't fully defined phi yet, okay? I'm going to define phi to be R cubed, sorry, phi of R cubed to equal A cubed, and I'm going to define phi of 1 to equal 1, okay? This is my definition of phi. Again, this is not part of the proof. I actually should have done this before the proof in the actual setup of phi. That's my bad, but I hope this isn't too confusing. This is part of the definition of phi, because when you define a map, you have to define what every element maps to. So this is part of our definition of phi. Now let's commence with the proof. So let's start with the left-hand side. Phi of R dot R cubed equals what? Okay, well, let's think. What's R dot R cubed? Remember, R is a rotation by 90 degrees, and then R cubed is a rotation by 270 degrees. So let's think. We have R, so take square, rotate by 90 degrees, and then R cubed, rotate by 270 degrees. So all the way to here, what happens? It goes back to itself, okay? What this means is that R dot R cubed equals 1, okay? So R dot R cubed equals 1. So I'm just writing that here. So phi of R dot R cubed equals phi of 1 because R dot R cubed equals 1. Okay, well, what does phi of 1 equal? Here, as part of the definition of phi, we said that phi of 1 equals 1. So phi of 1 equals 1. And I'm going to stop there. Now let's take the right-hand side. The right-hand side is phi of R star phi of R cubed. What does this equal? Well, let's think. What's phi of R? We define phi of R to be A. What's phi of R cubed? We define phi of R cubed to be A cubed. So this is A star A cubed. What's A star A cubed? Well, again, let's think. A is a 90-degree rotation, so rotate the cross by 90 degrees. A cubed is a 270-degree rotation. So if we do them both together, we do 90 degrees and then 270 degrees, we get the original cross back, okay? Which means that a star a cubed is actually equal to 1. And these two are the same. And so we've shown that the left-hand side does in fact equal the right-hand side. They're both equal to 1, okay? Now, for full proof, we will need to do this for every single combination of elements. But I hope that this example has shown how that works. And if you're really committed, you can go ahead and do every combination and show that it does, in fact, always work. Now, here's something interesting. This map here, we cannot construct a map that will end up being an isomorphism. So we can't construct a map that will satisfy this property for the rectangle. So this won't work for the rectangle group T that we defined here. Let me show you why. Okay, so now let's understand this notion of isomorphism at a bit of a deeper intuitive level by understanding why we cannot construct an isomorphism from these two groups of symmetries to the group of symmetries of a rectangle. So first, let's just quickly recount what we did. We had a map phi, and it mapped the element 1 in the group of symmetries of a square to the element 1 in the group of symmetries of a cross. It mapped R, so rotation by 90 degrees, to A, again, rotation by 90 degrees, but of different objects. And then R squared to A squared, and R cubed to A cubed. So then the question is, if there was an isomorphism between these two groups and the rectangle symmetry group, what would it look like? Well, we know that 1 will map to 1, okay? I'm not going to prove that, but that's a fairly easy fact to prove, which I'll leave you guys to think about, okay? But 1 will have to map to 1. If there was an isomorphism, 1 would have to map to 1, okay? What about the rest? Well, remember, what were the symmetries of a rectangle? Let's quickly recount. There was F, which is the horizontal flip, so flipping about the horizontal line. There was lowercase f, which is the vertical flip, so flipping about the vertical line. So we can capital F flip this way, lowercase f flip this way. And then there was also lowercase r, which was rotate by 180 degrees, okay? Well, naturally, we might think, and this isn't a formal proven statement, this is just going to be a guess from me, and I hope a bit of intuition from you guys as well to make this leap with me. But if there is an isomorphism, we would expect that the rotation by 180 degrees should get mapped to from the equivalent rotation by 180 degrees in these groups of symmetries. So what I mean to say here is that, well, for the group of symmetries of a cross, we have a 180 degree rotation. That's a squared. A squared is rotation by 180 degrees. So naturally, you might expect that a rotation by 180 degrees maps to a rotation by 180 degrees. So we might expect that a squared gets mapped to little r, so lowercase r, which is rotation by 180 degrees. Okay, we have two elements of this map. What's next? Well, now it's not so obvious because we're trying to map rotations into flips, okay? It's not so obvious, so let's give it a shot. Let's assume that a rotation by 90 degrees is a horizontal flip, so that's capital F, and that a rotation by 270 degrees is a vertical flip, so that's lowercase f, okay? So now we have our map, okay? And I'm going to call this phi 2, okay? Because these are two different maps. So now we have a map. Is this an isomorphism? My claim is that it's not. Why? So remember previously we knew that the group of symmetries of a square and the group of symmetries of a cross are the same because they satisfy this rule. So the rule is phi of r dot r cubed is equal to phi of r star phi of r cubed. So star is the operation for cross, dot is the operation for square, okay? So we showed this. Again, you have to show it for every combination of elements, not just r and r cubed, but if you do, then you've shown you have an isomorphism, and I'm not going to do that just to make the video a little bit shorter. So if this map is an isomorphism, if phi 2 is an isomorphism, so this is phi 2, then it should satisfy this, okay? It should satisfy the same rule, that phi 2 of a star a cubed, so a and a cubed, should equal phi 2 of a circle phi 2 of a cubed. So this circle is just the symbol I'm going to use for the rectangle group, okay? Because remember, every group has to have its own binary operation. In this case, all the binary operations are just actions followed by actions, so they all kind of mean the same thing in this context. So we need to show that this is true. The question is it true? Well, let's think. The left-hand side, so phi 2 of a star a cubed, well, what's that equal to? Well, a star a cubed is a 90-degree rotation followed by a 270-degree rotation. So if we rotate by 90 degrees and then 270 degrees, we just get the identity, right? We get a 360-degree rotation, which is just the identity. It's equivalent to doing nothing. So this is actually equal to 1. So then the question is the right-hand side equal to 1? Let's see. Phi 2 of a is, and so phi 2 of a composed with phi 2 of a cubed. Well, what's phi 2 of a? Phi 2 of a, so phi 2, a, it maps to f. So that's f, and then circle. So this is just actions composed with each other. So dot, star, circle, they all kind of mean the same thing in this context. So capital F, because 5a maps to capital F, circle phi 2 of a cubed. Where does a cubed go? Well, in our map, we define that a cubed goes to lowercase f. So it's just capital F to lowercase f. F composed by lowercase f. Well, what is this? Because this is supposed to equal 1, does it? So the question is, does this equal 1? Let's find out. So let's think about what f would do. So let's pick a vertex, okay? So this is our labeled vertex, okay? This blue dot here. What would f do, capital F? Well, capital F is a flip along the horizontal axis. So it should move the vertex here, right? So the vertex should go from here to here if we flip this way. Well, we have capital F followed by lowercase f. What does lowercase f do? Well, lowercase f flips this way, which means if we took the vertex from here to here in capital F, and then we flip it, so we took it from here to here, so I'm just writing it down here. If we flip it this way, it should go to here. So what does this mean? It means the vertex started here, and somehow it ended up here in the opposite corner. Is this 1? Well, no, because 1 is supposed to take the vertex to itself. It's supposed to start here and end here. So in fact, capital F composed with lowercase f does not equal 1. Okay, which means that this rule is not satisfied. Okay, the isomorphism rule is not satisfied. So please pause the video, sit back and think, and just ask yourself, why was this rule not satisfied? What was different about the rectangle? So I've gone back to our original page, and I hope you sat and reflected and thought about why the rectangle didn't work. And the key is that the rectangle does not have the same underlying structure as a square and a cross, okay? That's the reason, right? A square and a cross have the same underlying group of symmetries because the symmetries are the same. They work the same. You can do a 90-degree rotation and you can follow it by a 180-degree rotation. And whether you do that on a square or a cross doesn't matter. It's the same underlying structure. The difference was that a rectangle has a fundamentally different structure of symmetry. Even though it has 4 symmetries, just like the cross, right? All 3 of these groups have 4 symmetries, right? For the square, we have r squared, r cubed 1, cross, a squared, a cubed 1, and rectangle 1, r capital F, lowercase f. They all have the same number of symmetries, but the symmetries operate in a fundamentally different way. They interact with each other in a different way. And that's really what the study of group theory is about, what the study of symmetry allows us to observe when we look at symmetry through group theory. We see these underlying relations, this underlying structure. And that's why isomorphism is defined in this way, because when we define it as making sure that 2 elements compose in the right way on both sides of isomorphism, we ensure that the domain group, so the beginning group and the target group, have the same structure, that the map between the 2 groups preserves that structure, okay? So if a map preserves that structure, preserves the symmetry between the 2 shapes, then it's an isomorphism. And if we cannot construct any isomorphisms, so if we look at the cross or the square and we try to construct a map to the rectangle, to the group of symmetries of the rectangle, and we just cannot find any isomorphism, what does that mean? It means that fundamentally, on a very deep level, the symmetries of a rectangle are just not the same as the symmetries of a square, well, the rotational symmetries at least, and it's not the same as the symmetries of a cross. And because we found an isomorphism between the group of symmetries of a square and the group of symmetries of a cross, what does that mean? It means that fundamentally, those groups of symmetries are the same. It means that we don't really need to care about if we're looking at a cross, but if we're looking at a square or a cross, because the symmetries are the same. Okay, they behave in the exact same way. It's just really an aesthetic thing if we want to look at a square or a cross. Okay, and that's really the power of group theory and the power of the notion of isomorphism, right? Isomorphism allows us to look at objects and look at their symmetries and really kind of ignore those objects and really study the underlying structure of those objects. And in future videos, what I hope to explore is how we can actually apply group theory to many, many other things, because believe it or not, group theory isn't just about studying symmetries of shapes. It's actually about a much richer idea than the symmetries of 2D or 3D geometric shapes. Okay, there are many notions of symmetry in mathematics, and this is just one of them. And I hope I've given you guys a taste of what symmetry looks like and a taste of what it means for two objects to have the same underlying structure of symmetry.